Okay, so I'll just walk through one of these with you, and then I'll talk more about the other questions you had in your email. I just have a little topics listed here. This is similar to the first question you asked. It does have a stretch factor in front, this 3. So we'll just go through this one together, try to clarify things. This says consider the function f of x equals 3 times the quantity x minus 3 squared minus 1 passing through the point 2, 2. So forget about that for right now. If I first start just by looking at, I mean, you could just go ahead and graph this in the calculator, but if I start with the original parent function of x squared, I can kind of figure out what this is going to look like by first finding the vertex. So to find the vertex, I'm going to look at the numbers being added or subtracted inside the function or inside the parentheses and outside the function. So anything happening inside the function is a horizontal shift. So this minus 3 you would think would move me left 3, but horizontal always occurs opposite. So this is going to actually shift right 3 because of the minus. And the minus 1 outside will work the way you think it's going to work, and it'll go down 1. So instead of starting at the vertex, I'm going to go over 1, 2, 3, down 1. I'm going to start here. So that's why they give you this second point. They say it passes through the point 2, 2. So if I go over 2, up 2, my parabola is going to go through that point as well. So then I can kind of use the fact that parabolas are symmetric, and then I say, okay, well, if it's going through a point that's 1 unit over and 3 units up, it should be going through a point that's 1 unit to the right and 3 units up. So my graph's going to look something like this, and it's going to be messy because I'm not the best at drawing these on the computer, but it looks something like that. Okay, well, nothing like that. That's awful, but you get the idea. It's going to go through these 2 points, and there's the vertex. So then it says graph the function h if h is the graph of this shifted down 2 units. So to move this graph even further down 2 units, I'm going to have to subtract 2 more units from the outside. So I'm going to minus 2. So it looks like my function h is going to be, everything's going to be the same, but now I'm going to have minus 3 outside. Okay, so the turning point, if I move this down 2 units, is now here, which is going to be 3, negative 3. So we won't ask you any like complicated questions about stretching or compressing. That's why they give you this 0.22 to kind of like let you know you don't have to really worry about that too much. The 3 is what makes the graph narrower, but you can disregard it because we know a point that the graph goes through. So I wouldn't stress too much about the 3, okay, in this particular example. And then it wants to know the equation of h. Well, there it is. Everything's the exact same, except now we just have a further shift down, which is where the minus 3 comes from. Okay, if it said that it was reflected vertically, then this 3 would just be negative. That's all you would change. Okay, but really stretching, trying to figure out the graph from stretching is difficult because you can stretch a graph horizontally or vertically, and you can end up with an identical graph. So I have 3 graphs in my calculator just to show you. This y1, I'm going to actually, I have to make sure that they're selected again. So if I turn that one on, and I turn the original on, you'll see that if I hit zoom 6, the black graph, if I can make this bigger, let me see, large display. The black graph is y equals x squared. The blue graph is y equals, this is a horizontal stretch because I'm applying it directly to the x. So you'll see that I've stretched it out. Now, the same can be done by doing something to the outside of the function. So I put a 1/4 in front of the function. That's a vertical compression. So if I turn that on, you'll see I get the same thing. Watch, if I graph both, if I turn this blue on, you'll see that it's gonna show the same graph, but now the red's gonna get covered up with the blue graph. 3, 2, 1. The red got covered up with the blue graph. So they're identical. So oftentimes you can get the same graph by either performing a vertical or horizontal compression. So whenever they give you something that has that, they usually give you some point that the graph goes through, so you don't really have to worry about the compressions too much. Okay. If you're ever looking for a second point to graph it, you can always, like if they gave you this and said, graph this down here, and you're not sure what the 3 is going to do, what I would do is just throw it into the calculator. So let's just say that, let's say the question was, graph this function below. Okay. Yeah, there's a shift, but you don't really know what the 3 does. And let's say they didn't tell you a point that it went through. What you could do is just put that whole thing in the calculator. So if I plug this in, I have 3 parenthesis x minus 3 squared minus 1. And I'm going to hit zoom 6 for a standard window. So there's my graph. So you could use the translations to say, okay, the vertex is over 3 down 1. So there's the vertex right there. So if I hit trace and plug in an x value of 3, I'll see that the vertex is 3, negative 1. And then in order to graph it in Canvas, all you need is another point. So you could just pick a number next to 3. So you could type in 2. You say, oh, it goes to the point 2, 2. You could plug in 4. Oh, it goes to the point 4, 2. So that's all you would need. You would just hit the vertex and then 4, 2, and then the computer will graph the entire thing for you. So I wouldn't stress too much about compressions, really. Just know that adjusting this number will result in a stretch or a compression. That's all you really need to take away from it. Okay, as far as radicals, I think your question was about flipping radicals vertically or horizontally. So if I have a graph, let's say I have the graph, this is again going to be a rough sketch. This is the graph f of x equals the square root of x. Again, if I apply a negative to the outside, if I did this, let me change the name, g of x equals negative x, square root of x. Well, that would take all the y values and make them negative, so the result would be this. It would be a vertical flip. Now, if I wanted to make a horizontal flip, you apply it inside the function. So h of x equals the square root of negative x. So that would take the original and flip it horizontally, so you would get that. So then you go, okay, well, how can you have negative in the square root? Well, think about it. If I look at let's get rid of this middle one. If I look at this graph, I can plug in x equals 5. If I plug in x equals 5, I get the y value is the square. I should have picked a better number. Maybe just pick up easier numbers. We don't have to do the ugly decimals. If I say x can be 9, and then I plug 9 in, I get the y value is 3. So this graph is going to go through the point 9, 3. I can't plug in 9 here, because that'll be the square root of negative 9, which gives me 3i, which is imaginary. So this graph doesn't go over here. But I can plug in negative 9 here, right? If I did that, h of negative 9, then I would have the square root of negative 9, which is the square root of positive 9, which is 3. So this graph goes to the point negative 9, 3. So you can have a negative in the square root. The only thing you have to worry about is that will affect your domain. So your domain has to be all numbers such that whatever is inside here remains positive. So negative x is fine in a square root as long as x is less than or equal to 0. If x is less than or equal to 0, then this is always going to result in a positive number. That's why the graph looks like this. Starts at 0, goes to the left. Okay? It's not defined for positive numbers because you're right. You'll end up with one of those imaginaries. And I think the last question was about composition here. So if they give you the generic function, they say find f of g of x, then you're going to have to plug g of x into the function to figure it out. I think the confusing part here is that g of x is just 2. So no matter what x is, g of x always spits out 2. So when it says find f of g of negative 3, the first thing you can do is, well, what is g of negative 3? Well, g of x is always 2. That's just going to be 2. So then this says plug 2 into f. All right, well, f of 2 is 5 times 2 minus 5. That's 10 minus 5, that's 5. Now if I do the reverse, g of f of 4, that's 5 times 4 minus 5, that's 15. G of 15, well, g of x is always 2, so you just get 2. I think that's what confused you probably. It's just that 2 there.